Good evening. Hello everyone. Electric field. Is it like gravitational field? There will be attractive nature only. This electric field, there is one similarity with gravitational field, that is extends up to infinity. Field and field strength. These two terms you have to learn properly. Field means, let me explain, with two stationary charges in vacuum, Q1 and Q2. The force of interaction we have seen before, Q1 Q2 by 4 pi E0 R square. This force, like whatever is, like gravitational force, we can see this one, this A vacuum, as a two-step process. What are those steps? Imagine Q2 affected by Q1. Q1 is heavy, Q2 small. Q1 will affect Q2. But is there any change of force? No. Force will have the same value. They will experience the same force. But we are assuming it created, it will interact with charge Q2. So what's happening there? Q1 creates something in its surrounding that is called electric field, and that field is responsible for the force of interaction between two charges. Okay? So electric force of interaction can be seen as a two-step process. What is that? Step 1, the charge creates something in its surroundings, and step 2, this something will be referring as electric field. This something I told, no. This something stands for field, electric field. This something is called electric field. Okay? Then the field, something is surrounding means electric field it creates. Now step 2, what happens? This field is responsible for force of attraction or repulsion. Force of interaction due to this field. Clear? So when you are starting a chapter, starting a topic, then some assumptions are always made. That force of interaction we are seeing a two-step process. A charge creates something in its surrounding, that is field, electric field. Then field is responsible for field exert force on it. I am a poor man, I don't have any field. A rich man like Elon Musk, he has field extended all over the world. But he says that matters. This is the field of Elon Musk. I listen to him. So he has influence on me. Isn't it? That's why I'm listening to him. So he creates his field and that field affects electric field like that. A charge will create something in surrounding. That something is electric field, then field will exert force on you. Now the question is, the field will be extended up to what distance? Up to what distance this interaction force exists? This electric field extends up to infinity. Theoretically, wait with me. Theoretically, the field extends up to infinity. But practically, its influence is felt over a limited region only. Okay? If you keep a charge here and go 10 kilometers away from it, then it has no influence. If it is close to the charge, then it has influence. Okay? So how can I define electric field due to a charge? Formal definition will be this, we are doing it for a point charge. Electric field, note the statement, electric field due to a point charge is the region of space where its influence is felt by some other charge. So be careful about this. It is a region of space. Whole region. And it's a common experience. If you assume that there are two charges, Q and Q0, and assuming Q has influence on Q0, if Q0 close to Q, then force increases. Q0 away, the force decreases. And the electric field it creates extends up to infinity. Isn't it? We need to measure the magnitude. Field is the region of space. But its strength will be how much at certain distance that we are going to find. It's a practical problem, I am telling you. We are going to measure the magnitude of field, electric field. Obviously, it's a measurement. It is not theoretical statement only. Electric field due to point charge, how does it vary? It has a measurement. This measurement cannot be done by a superior charge. Why? Due to the action of superior charge, if Q0 is superior, then Q will be affected. When a force created by Q will be affected. Field created by Q will be affected. So, what we'll do here, this Q0 will assume a very small charge. And we are going to calculate the strength of electric field due to this charge Q, point charge. Theoretical definition I tell you, assuming Q0 is very small. Assuming Q0 is small, we can replace Q0 by delta Q. Okay? Then we define strength of electric field. And this delta Q is very small, it is tending to 0. Strength of electric field due to a point charge is equal to force experienced by a vanishingly small test charge per unit charge of it. Okay? Force experienced by vanishingly small test charge per unit charge of it. This del Q tending to 0. This del Q we always have to take very small. This del Q will be referred as test charge. And this Q will be referred as source charge. Source charge may be anything. Source charge may be point charge, maybe continuous distribution of charge, maybe volume distribution of charge. But the test charge has to be very small. Why it will be very small? It's a good question. Because otherwise, it may affect the field created by the source charge. We are discussing the effect of source charge. By using what? By using a very small test charge so that field created by Q is not affected. Yes. Vanishingly small test charge per unit charge of it. This we are defining. Vanishingly small test charge we are defining here. Strength of electric field we are defining. Vanishingly small test charge also definition. We have to go by this definition. It is defined as. Okay. So can you tell me what's the expression going to be if they are separated by distance r? We want to measure the magnitude of strength of electric field due to the charge Q. How do I find? You have to go by this definition. It is measured by force experienced by vanishingly small test charge per unit charge of it. Now, source charge Q, test charge del Q, and we want to find at a distance R the strength of field. So let separation be R. Force will be how much? KQ into del Q by R square. Agree or not? So F by delta Q is what? KQ by R square. Limit del Q tending to 0. By definition, E equal to KQ by R square. Strength of electric field is KQ by R square. So if a charge Q is there, due to this, the strength of electric field will be now one thing you need to make very clear. Q and delta Q, what way they are exerting force on each other? Q on del Q on Q, along what direction? Line segment joining these two. Because of vector form of Coulomb's law, we have decided in the last class. This is the importance of Coulomb's law. So this electric field E is a vector quantity directed along F. Okay? R is there. Can define R cap. If we write the vector form now, we are writing the vector form now. Huh? This we are rewriting. Which one? This one. You do it with me, you will remember everything. A vector is what? Tell. K into del Q by R square. I mean KQ. How will I write? I showed you the vector form. R cap. Isn't it? This is R cap. So scalar to vector we are going. F by del Q. KQ by R square R cap. Limit del Q tending to 0. By definition, this is RE. Now this is perfect. This is perfect now. E equal to KQ by R square into R cap. Okay? So at a distance R, the strength of the electric field is KQ by R square. Direction along the line segment joining two charges. Isn't it? Now, the source charge Q, I told you it may be positive, may be negative. This charge Q may be positive, may be negative. Del Q is never negative. So this also is keep in your note. The test charge is small, anything small you can say, and always positive. But Q is what? Q may be positive, may be negative also. Am I correct? Q may be positive, Q may be negative also. So now, just tell me one thing. Suppose Q is positive. Then field at this point will be directed in what direction? Delta Q positive. In what direction it will experience force? Tell away. If Q positive, write your conclusion. If Q is positive, then E is radially outward. Okay? But if Q is negative, for positive charge is radially outward. For negative charge, E will be directed inward. P. Del Q. Per unit charge, the force is inward. Q is negative, then E is directed towards the charge. Clear? Understood? Now, so I have told you one thing. There is a charge and its electric field at some distance is E. Okay? Just write in the form of question. There is a charge Q. And the strength of electric field at some distance away from it is Q, is E. Charge is Q. Some distance away from it, the field is E. My question for you, can you tell me the force experienced by charge Q placed here? The question is what you understood, I hope. There is a charge Q. Strength of electric field at a distance, at some distance away from it be E. Then, what is the force experienced by another charge Q placed over there? Simple. This is the strength, you know. This is what? Force experienced basically per unit charge. Am I correct? So due to this charge Q is what? By unitary method, force will be what? Q into E. Okay? If Q is positive. Now this is not our test charge. This is a charge Q. How much force it will experience? I can tell this one is either positive or negative. If you got a QE, if Q is positive. And Q is positive in what direction? Radially outward. If Q is positive, F equal to QE inward if Q is negative. Understood? That's all about the force experienced by charge when it is placed in a electric field. So one thing be clear. E stands for what? E stands for force experienced by, when you are writing in your board or school paper, you write it is force experienced by vanishingly small test charge per unit. But when you are solving a problem, what is in your mind? What is in your mind? When you are solving a problem, it is force experienced by unit charge. Okay? Like superposition principle here also it exists. At a point due to many charges, field will be resultant field. Okay? So we'll do that. Before that, just write a question here. There is a point charge 2 × 10⁻⁻6 coulomb. There is a point charge q × 10⁻⁻6 coulomb. Find the force experienced by it when situated in an electric field of strength 50 Newton per coulomb. Unit will be this, no? Because F equal to QE. You've just seen magnitude. So E is what? F by Q. F is in what? F is in Newton. So it will be Newton per coulomb. U will be 50 Newton per coulomb. Then what is the magnitude of force experienced by this charge? This charge situated at a point where electric field is this. What is the magnitude of force experienced by it? So simple. Simple. Force will be what? Answer. Q is this. Q into E. That is okay. Now I am taking another problem for you. Number 2. There is a ball of mass m. Okay, very simple question. Length of the cord is L. It's a charge Q. Okay? Positive. I did not give negative charge here. When horizontal electric field is applied, find the angle of deviation when horizontal electric field of strength E is applied. Have I done properly? You have understood, I guess? Huh? Now it is situated in electric field, horizontal electric field, strength E. This. I'm just showing the direction, nothing else. Electric field has a direction, no? I'm showing you that. What is the angle of deviation of the thing now? We have done this kind of thing in Coulomb's law. So apply a little bit concept here. You go by force calculation. This, do you think it will remain stationary? No. Even if it's positive, away. So suppose due to the field, it is now situated like this. Bob's mass given, so don't hesitate. with mg acting, tension be T, so T has component. This way it will be T sin theta, this way it will be T cos theta, isn't it? So go by equilibrium condition again. What is the force here? Tell. Q into E, agree or not? So for equilibrium, T cos theta mg am I correct? Okay. Theta we have to find, just divide. Dividing 2 by 1, tan theta will be dV by mg. So theta will be what? Okay. You have understood? Now just another very simple problem I would like to explain. Number 3. An oil drop of charge Q and mass M is in equilibrium in air. By applying electric field of strength E. Okay? By applying a vertical electric field, but direction I am not telling, of strength E. Find the magnitude and direction of P so that find the magnitude and direction of P. This is my question. Okay? Obviously, one question arises from your side that oil drop has a charge is positive or negative? Oil drop charge is negative. Okay? Okay, I am telling you this one is extra fact. Assume charge on oil drop is negative. Now can we explain by using your concept of electric field? This oil drop is floating. Charge Q. And it is negative. So in what direction field is applied and its strength so that it is stationary. Upward. Just make one thing clear. Electric field is the force experienced by vanishingly small test charge, which is positive. So A positive charge move along the direction of field. Negative charge opposite. So better you have a note on it first, or this is your own clarification. A positive charge, a positive charge is a known fact. A positive charge moves along the field, and a negative charge and a negative charge moves opposite to the direction of E. Am I clear? No, no, no. Listen to me carefully. We have taken the test charge always positive. That's why field at a point directed in the direction where positive charge experiences force. So field is always along the direction of motion of positive charge. If a positive charge is kept. Electron if you give, it starts moving opposite. Here, never problem. Positive charge will move along field, negative charge against the field. Here, so what will happen there? Oil drop, negative. What is the mass? M. Weight in what direction? Downward. Electric field? Sure. Because negative. If you don't apply downward, you will not experience upward force. So that will clarify, right? Field has to be applied downward direction so that charge experience force upward direction. For equilibrium, QE equal to mg. So direction we have clarified first. Now magnitude. Okay. Now, unlike superposition principle in like or not like, superposition principle in Coulomb's law, in case of electric field also superposition principle is there. Superposition principle. Electric field strength at a point due to various charges is the vector sum of electric field strength at a point EFS at a point due to several charges is the vector sum of all the EFS due to each individual charges at the point. Have I done correctly? Many charges are there We want to find strength of electric field here. This Q1, Q2, Q3, Qn. N charges are there. So E will be what? Take the sum. Q1 plus E2 to En. Okay? So net field will be the vector sum. Similar problems will arise here also. Let us start with the easiest one. Number 1. Q Q and 2Q. A, B, C. Okay? Find the strength of electric field at the midpoint of line segment joining these two charges. D. If charges are situated at the vertices of equilateral triangle of side A, find electric field strength at A. This you have to find. Find EFS at D, midpoint of AB. Will you try? You try. I am also doing. Then check with my calculator. So one simple thing you have to keep in your mind. Force explained by vanishingly small test charge for writing answers, theory answers in board paper or school paper. When you are solving a problem, what will you keep in your mind? It is the force experienced by unit charge. So I just imagine a 1 coulomb charge placed here at this point. Just imagine 1 coulomb charge is kept here, this point. Okay? So this is simply force experienced by 1 coulomb charge, nothing else. So due to 2Q, and due to this Q, what will be the direction of field? Tell. A by 2. This is also A by 2, agree or not? Yes. So field due to A here, if we take it as EA, and due to B here, EB, they get cancelled. Magnitude of EA, magnitude of EB, AQ by A by 2 whole square. Formula you know. So what is your comment? Therefore, EFS at D due to A and B gets cancelled. So due to 2Q only it will exist. How much? So electric field at D is due to 2q at C. This is given by what? E at D will be what? Due to charge at C, del 2q by K into 2q by what's the distance? Root 3 by 2a. So K into 8q by I can simplify more. Magnitude will form. Two-third I hope you have understood. Huh? Next session we will do it for continuous distribution of charge. It's for point charge. A little bit idea you have. When problems will be solved, you will understand better. Okay.